We cross them every single day, these massive structures of steel and concrete that we totally take for granted. But here's the thing, like anything, bridges get old. They can develop problems that are completely invisible. So how do you find a fatal flaw before it's way too late? Well, it turns out you listen to its heartbeat. And the stakes? They couldn't be higher. This quote really just gets right to the point. We're not talking about simple maintenance schedules here. We're talking about preventing an absolute catastrophe. The real challenge is that the most dangerous threats, they're almost always the ones you just can't see. So that's the big question for us today. It's kind of like a detective story, right? The clues are there, but they're hidden deep inside the structure. To find them, engineers had to get creative and develop a way to see what's going on inside without ever picking up a hammer. To really understand the solution, first we have to appreciate the problem. And the problem is that the real danger lies in damage that's completely hidden from view. And look, these are not theoretical risks. These are real. The Miamis River Bridge, it collapsed because a single hidden steel pin failed. The Schoharie Creek Bridge was literally undermined by water washing away its foundations from below. And in Rhode Island, a total disaster was avoided by pure dumb luck when someone just happened to spot a crack. These events prove it. What we can't see can absolutely hurt us. So here's the bottom line. Visual inspections are, of course, absolutely essential, but they have their limits. An inspector can't see the corrosion happening deep inside a concrete pillar or the erosion of a foundation buried under a riverbed. They need a new sense, a way to perceive the bridge's internal health. And this brings us to a really fascinating concept. What if a bridge could just tell us when it's sick? Well, in a way, it can. Every single bridge has a unique, secret heartbeat. The key to this is something called natural frequency. Everything has one. If you've ever tapped a wine glass that specific pitch or rings at, that's its natural frequency. A bridge does the exact same thing, just on a massive scale. It vibrates at a set of unique frequencies when it's pushed around by wind or traffic. It's the bridge's own vibrational signature. And here is the crucial connection, the big aha moment. That signature changes when there's damage. Think about a guitar string. If you loosen it, you're reducing its stiffness. And what happens? The pitch, the frequency, drops. The exact same principle applies to a bridge. A crack or corrosion or a weakened foundation, it makes the whole structure less stiff. And this chart lays it all out perfectly. A healthy, stiff bridge has a higher natural frequency. But when damage happens, the stiffness goes down, and that frequency, the bridge's heartbeat, slows down. So, by measuring this frequency over time, engineers can spot a change that screams, hey, there's a problem here, long before it ever becomes visible. Okay, so if a bridge has a heartbeat, how on earth do engineers actually listen to it? Well, they need a kind of structural stethoscope. It really boils down to a two-part strategy. First, they have to listen to the actual bridge out there in the real world. And second, they create a perfect, healthy version of that same bridge inside a computer, so they have something to compare it to. The real-world measurement is called an ambient vibration test, and it's actually surprisingly straightforward. Engineers place these super sensitive sensors, called accelerometers, at key spots on the bridge. And these things are so precise, they can measure the tiniest, most imperceptible vibrations from everyday traffic and wind. They just listen, they record, and then they analyze that data to find the bridge's signature frequencies. Now, the second approach, this is where things get really high-tech. Engineers create what's called a digital twin of the bridge. They do this using an incredibly powerful simulation technique called the finite element method, or FEM. You can think of it like building the entire bridge out of thousands of digital Legos, or elements. The computer knows the properties of the steel and concrete for each little piece, so it can build a perfectly accurate virtual model. And from that model, it can calculate exactly what the bridge's natural frequencies should be in a perfectly healthy state. This gives them that vital, perfect baseline. So now we have two sets of data, the real-world heartbeat from the sensors and the ideal heartbeat from the digital twin. This is where the magic happens. This is where the diagnosis begins. The entire process, everything we've talked about, hinges on this one comparison. If the measured frequency from the real bridge is lower than the calculated frequency from the healthy digital twin, that is a clear warning sign. It tells engineers that the bridge has lost stiffness somewhere, and they need to go find out why. And this isn't just a theory. You might be wondering, does it actually work? Oh yeah. Just look at this data from a Federal Highway Administration test. They measured the frequency of a bridge support pile when it was perfectly intact, 21.88 hertz. Then they simulated foundation damage by digging around it. The frequency dropped. Finally, they actually broke the pile, and it dropped again. A clear, measurable drop for each stage of damage. It's undeniable. But how do you actually get that single, clean number from a messy, noisy vibration signal? Well, engineers use this powerful mathematical tool called the fast Fourier transform, or FFT. The best way to think of it is like a prism. Just like a prism takes white light and splits it into all the colors of the rainbow, the FFT takes a complex vibration signal and splits it into all the individual frequencies that make it up. It lets engineers see that signature heartbeat, loud and clear. Of course, this whole method is only as good as that computer model, right? I mean, how accurate can it be? The answer is remarkably so. This data right here compares the predicted frequencies from the model to what was actually measured on a real bridge at different speeds. I mean, look at them. They are nearly identical. That gives engineers tremendous confidence that this process works. So, what does this all mean for the bridges that we rely on every day? It means we can finally move from being reactive, waiting for something to break, to being predictive. This technology is an absolute game changer. It lets us find that hidden damage before it leads to a collapse. For a country with tons of aging infrastructure, it helps officials figure out which bridges need repairs most urgently. This shift to predictive maintenance saves a ton of money and, most importantly, extends the safe lifespan of our vital transportation links. It's literally paving the way for a future of smart infrastructure that can tell us when it needs help. And that really leads to one final mind-blowing thought. We've gone from listening with temporary sensors to understanding a bridge's health in incredible detail. So what's the next logical step? Giving our bridges a permanent nervous system. Could we build new structures that come with sensors already embedded, constantly monitoring their own heartbeat and alerting us to a problem the very moment it begins? All the technology is telling us the answer is a resounding yes.